Hi everyone, I hope you're enjoying your snow day. But we're going to continue with our lecture that we started on Monday, which was chapter 10, when we started our discussion about gases. So excuse me if this is a little bit choppy. I'm just trying to get this to work today. There we go. All right. So last time, so on Monday, we derived 4 different laws in which we were able to relate different variables of the gases, either pressure, volume, the amount of the gas, and the temperature, to different behaviors of gases under different circumstances. And those were Boyle's law, which related P and V, so we knew that the pressure is inversely related to the volume as long as the number of moles of the gas is held constant, as well as the temperature is held constant. Charles' law told us that T and V were directly proportional as long as the number of moles of gas and the pressure of that system was held constant. Those two laws, Boyle's law and Charles' law, were combined into, at the aptly named, combined gas law, in which P, V, and T were all related to a constant. So it's P times V over P times V over T is a constant as long as the number of moles of gas was held constant. If we kept the volume constant of that system, then we knew that P and T were also directly related as long as N and V were held constant. The last one that we talked about was Avogadro's law. The same guy who will get the name for Avogadro's number related the number of moles and volume, in which volume and moles were directly proportional as long as P and T were held constant. And so we had basically a bunch of equations that described the behavior of gas under very specific circumstances. What we're going to find out today is actually, even though we have all of these equations, they can all be combined mathematically into one new equation. And this equation is called the ideal gas equation. So it combines all the other gas laws into a single equation. So you can see we have our pressure, our volume, our number of moles, we'll skip R for the time being, and we have our T as temperature. So we have this relationship that we see between these 4 variables that we were discussing before. So we have this other variable that just popped up out of nowhere, at least seemingly, which is R. So R is the universal gas constant. And so when we were talking about constants before, when like P times V equals a constant, so if you notice that the equation we have right there, P times V equals nRT, if we remember Boyle's law, N and T are being held constant, and P times V equals a constant, so we can lump all 3 of those together. So there's our constant moles, our constant temperature, and that constant we had before, which is a proportionality constant, and this is what is relating the P and V to that unnamed constant we had before. So we're able to combine this into a new equation. So PV equals nRT, with R being the universal gas constant. So like we discussed before when we were talking about pressure, I said we need to know pressure in terms of atmospheres, or millimeters of mercury, or torr, or bar. They gave different numerical values, but they're all representing the same phenomena, right? So if we have 1 atmosphere of pressure, so we're standing at Boston Harbor, so at sea level, 1 atmosphere of pressure. We also know that 760 torr. 1 and 760 are different numbers. We're pretty in tune with that, but they're different units. And the same idea applies to R. So you see on the right-hand side of the screen, we have R. So even if you Wikipedia this, you're going to find out R has a humongous table. All of them are representing the same concept of R, this universal gas constant. Depending on what units that you use, it's going to change the numerical value that precedes the unit. For right now, until pretty much I think we get into 1102, we'll be continuously using this top value for R, which is R equals 0.0820758 liter atmospheres per mole Kelvin. So as I was saying before, any of the gas laws can be derived from the ideal gas law if the other 2 variables are held constant, right? So what I want to try first is to derive Charles' law, which relates T and V. So let's think about that. If I have some system, doesn't matter what, where I can describe the gas in terms of P, V, N, and T, where R is this universal gas constant. So there's some P associated with the system, some volume associated with the system, some number of moles of gases of that system, and that system is at a certain temperature. We can also change that system because we can either vary the pressure, so P2, we can vary the volume, V2, we could vary the number of moles in that system, N2, or we could change the temperature of the system. So essentially we're looking at the same thing, it's the same objects, we're just changing the variables that can describe that gas that's in that system. If we rearrange those equations in which R is isolated by itself and all the other variables are on the other side of the equation, we see that both of them actually come out to the same thing, which we'd expect, where R equals P1 times V1 divided by N1 times T1. That's describing condition 1, or in condition 2, where R equals P2 times V2, all divided by N2 times T2. So let's think for a second. We have two conditions, and we're noticing we have two different equations, but both are related by that same universal gas constant, R. So what we could do is set each equation equal to each other through R. So now we have this overall equation of P1 times V1 divided by N1 times T2 equals P2 times V2 divided by N2 times T2. So this is going to be really powerful for us because we had, I think, 4 different equations we had before. If we go all the way back and look at our chart, we have several different equations. Sometimes it's like, wait, do I use Boyle's law? Do I use Charles' law? Do I use the combined gas law? Do I use Avogadro's law? That can be a lot to interpret and to decide on a quiz or a test or in real life if you're working in the lab, what equation am I going to use? The interesting thing is you can always use this equation, and we're going to come back to an example where we do that. But the first thing I want to do is let's finish off deriving Charles' law. But I'm going to tell you right now, as a heads up, that what we've derived right now is a pretty powerful equation. So we'll continue with that equation, right? And we got to remember what Charles' law relates. And it relates the volume of a system and its temperature while keeping the pressure of the system and the number of moles in that system constant. So we can rewrite that in a mathematical sense, a logical argument, saying that constant P, and then you see this triple dot right here, that means therefore, so constant pressure, therefore, pressure 1 equals pressure 2. Pressure 1 equals pressure 2. Also, constant N, so constant number of moles, therefore, N1 of the system equals N2 of the system. N1 equals N2. So we take a look at that. That means P on both sides are equal, so let's get rid of those denominations of 1 and 2, so it's just P. Same idea with N. We don't need the denomination of 1 and 2, it's just N because it doesn't change. What we notice then is that P is on both sides of the equation, N is on both sides of the equation, and then they cancel out. I know that kind of looks like an X, but it's an N with a cross through it. That simplifies to V1 over T1 equals V2 over T2. And if you take a look at your notes from Monday, there's Charles' law, which explicitly stated as long as we were comparing V and T and kept P and N constant, well, this is our relationship. So we can see how the the ideal gas law ends up being really powerful, because as long as we know what we're changing, the V or the T, and what we're keeping constant, the P and the N in this case, we can just use the ideal gas law and derive all those other equations that we talked about the other day. So let's use the ideal gas law in an equation, in a real life situation. So our problems are going to start to get a little bit more complicated because the way that they can be phrased, the number of variables that we're using, are going to grow in just the number of variables that we have. So I'm going to show you a system, and we've used it before, of organizing, taking our paragraph form questions and turning them into simpler variables. So let's read through this. It says, how many moles of oxygen are there in 50 liters of a gas cylinder at 21 degrees Celsius when the oxygen pressure is 15.7 atmospheres. So sometimes having words can be not difficult to wrap your head around, but it's not as easy for your brain to immediately pick out what the variables are and what we're solving for. The best way to do that is to make a column of givens, finds, and then usually what I try to encourage my students to do is make a third column for just equations that we could possibly even think we might use, right? We're starting chapter 10. It's kind of, we're in a very scaffolded type of environment, so we probably realize what equations we're going to be using. But in real life, sometimes you don't know, and sometimes you just need to say, okay, this is what I'm trying to find. These are some equations that I know. What could get my mind jogging to think of it? What can I go in the right direction of how to solve this problem? So we go through the problem, right? Well, that's what's asking us to find, blah, 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 blah. Okay, they're in a 50-liter gas cylinder. So I know the volume of my cylinder is 50 liters. So V equals 50 liters. At 21 degrees Celsius, well, there's my temperature. T equals 21 degrees Celsius. I've already described the gas inside the cylinder as oxygen, so the pressure is 15.7 atmospheres. There we go. Pressure equals 15.7 atmospheres. I've already pre-written down R, because usually when you start dealing with gases, it's, let's just put it down there. I'm not always going to give you R. It's going to be your responsibility to realize that, oh, if I'm dealing with gases or I'm dealing with certain equation where I need R, it's my job to go and find R. And usually on a quiz or an exam, R will be on the back page in a list of constants that I would give you. But as I'd shown before, I can give you few different types of R's. So it's not necessarily always going to look like this. So you're going to, with the liter atmosphere per mole Kelvin, it'll be up to you to determine which quote unquote, I guess, R you're going to be using. They're all the same R, but they have different numbers and different units. So we're done with our given column now. So we're asked to find, it's saying how many moles of oxygen are there in 50 blah, blah, blah. That's our description. So we're looking for the N, so number of moles of O2. So N sub O2. And again, I already kind of gave that away. Maybe you make a list of equations that you think you might need. We're a bit scaffolded here because we're just dealing with chapter 10. It's just the beginning. So let's write down PV equals nRT. So we have our givens to remind ourselves. We have our equation PV equals nRT. So let's take a look at what we have and what equation we think we're going to use. Do I have P? Yep, I do. Do I have V? Yeah, I do. Well, I need to have one unknown or else it's dumb to use the equation. So N is my unknown. R I also have and T I also have. So that's great. I basically have one equation, one unknown. That is entirely solvable. So let's do that. We rearrange the equation to get N and isolate that variable by itself. So we divide both sides by RT. So we end up with PV over RT. And let's take a look. Let's throw in our numbers and see if we can just dump this into our calculator. So we got 15.7 atmospheres, we got 50 liters, we have our R, we have our T. But what you're going to start to notice when we have more complicated equations or we are using a lot of variables with different units, sometimes we need to double check our units. Because if we take a look, basically, R is defining what units we should be using. We should be using liters, atmospheres, moles, and Kelvin. Well, there's my liters, there's my atmospheres. I'm searching for mole. Well, I'm in degrees C. That's not quite what I'm looking for. So a lot of the time what I do when I'm using, especially if you're doing something new and you need to make sure you're going in the right direction, do unit analysis. Get rid of any numbers that you were using and just deal with the units that were associated with those numbers. So if we take a look at that, originally we arranged everything so N equals P times V divided by R times T. So let's take a look. Well, my P had units of atmosphere, my V had units of liters, there's my units for R, and there's my units of T that I was trying to plug in. What I'm going to do is I'm going to separate these three variables into their own fraction. It becomes a little bit more difficult when you're dividing by a fraction. My recommendation is start playing around with real fractions and figure out what ends up happening to these units. But I'll tell you right here, if you have a fraction within a fraction, you actually take the reciprocal and it can come out like this. So you notice liter atmospheres on the top of this fraction, so the numerator, divided by moles Kelvin. We go over here, it flips, mole Kelvin on the top, liter atmospheres. It's the same exact mathematical operation. I recommend, again, go prove it to yourself if you don't, not even if you don't believe me. Sometimes it's just good to get in the practice of it. But if we see here, atmospheres on the top, atmospheres on the bottom, they'll cancel, liter and liter. Well, degrees C and K don't cancel. We'd end up with N in units of mole Kelvin per degree Celsius, which is not a useful unit of number of stuff. We want N to be in units of moles. So what we need to do, and this is my recommendation for any time you're dealing with any gas laws, convert your T immediately to Kelvin. And it looks like it didn't scan too well. Maybe you guys might see that. That's supposed to be a dot right here. So we're converting 21 degrees Celsius into Kelvin. It's 294.15 Kelvin is our new T. We'll take a look. We'll dump everything in. We've already checked our units before. We know the kelvins will cancel out. We should end up with units of just moles. At this point, it's just putting in the numbers into your calculator, and you should end up with 32.5 moles of oxygen gas. They're in this 50-liter cylinder of gas cylinder, at 21 C at 15.7 atmospheres. So sometimes it's a lot of words, but if you break it down into givens and finds, it makes your life a lot easier. So what I want to do now is give you an example where we use the ideal gas law, but in a way to compare two different states. Kind of like when we were talking about before, when we were talking about the other four gas laws, where we'd say, okay, if we were dealing with, let's go all the way back, if we were dealing with Boyle's law or actually let's just do a Charles law because it's here, right here, and we see that when we have a volume 1 and a T1, so that's a condition 1 equals some condition 2 where we have a volume 2 and a T2. This is what I mean by a comparative ideal gas law example. So we're going to try to use the ideal gas law from situation 1 compared to situation 2 and determine an unknown variable. So let's read through this. It says the total volume of oxygen gas that can be obtained from a particular tank, so we just have a certain tank, it's at 1.00 atmospheres of pressure. It's initially at a temperature of 21 degrees Celsius and has a volume of 785 liters. What would the volume be at 28 degrees C if the pressure is kept constant? So again, we have a word problem. I recommend making a list of givens and finds. So the pressure is at 1 atmosphere. We are also told at the very end of the equation, or the end of the question, that if the pressure is kept constant, so pressure is constant, so we know in situation 1 it equals 1 atmosphere, and also in condition 2 it equals 1 atmosphere. T1, it says we started at 21 degrees Celsius. I immediately converted to Kelvin because I'm thinking gas laws. Let's not even deal with the simple math. Let's just put it right into K right away. My initial volume, which is my V1, and again, these subscripts do matter because it's saying when I had this volume of 785 liters, that is corresponding to the temperature 1 at 21 degrees Celsius. So I couldn't just call this T2 arbitrarily. These two need to be linked because they are describing the same situation. Then it says what happens, so what happens to the volume, V2, so we're talking about a second situation, a second condition, when we change the temperature to 28 degrees Celsius. And again, let's not even think, let's turn that directly to Kelvin of 301.15 K. All right, so we said we have basically two paths to answer this problem. The first, we can immediately recognize that, oh, it's a Charles law problem. Well, that's not always that obvious. Sometimes it's kind of difficult when someone just gives you a real life example, like, I have a bunch of gas laws, which ones do I use? What I tend to use, sometimes maybe you'll recognize it right off the bat, make your life real easy, go for it, you recognize it as Charles' law, plug it in. The way I go about it in a more systematic way is to always start with the ideal gas law, and this is what we're going to start with. We're also going to make a list of assumptions too. So this is what we've already kind of said here in our givens, where pressure is constant, therefore pressure in condition 1 equals pressure in condition 2. So the way you can imagine this is that if you have a tank, but imagine one of the walls is a piston, so it's slidable. So if we want to keep that pressure constant, that means that little piston can either slide up or down, and that's going to change the volume, but it will keep the pressure always the same on the inside. So we can assume our pressure is constant. This one is a little bit less intuitive, and sometimes you need to really fully understand and think physically what the question is asking. It's saying I have a tank. You think about like a scuba diving tank, right? It's not letting water into the tank, so the number of moles of stuff that is inside the tank is kept constant unless you breathe it out. So assuming this is not like a scuba tank where moles of gas are being sucked out so you can breathe, but instead it's like when you go into the lab and you see a tank of gas just sitting there, right? We can assume that N, since it's a sealed container, so N is constant. Therefore, the number of moles we start with in condition 1 has to be the same number of moles that we end with in condition 2. So now it wasn't explicit in the equation, or at least in the question, but we made a really reasonable assumption. So let's see if we can put this all into play. So again, kind of like when we were deriving Charles' law, we have a situation 1, so condition 1, and we have condition 2. Conveniently for us, when we look at PV equals nRT, PV and a T can always change, but R is a constant. So if we solve for both conditions in terms of R, here's our condition 1, here's our condition 2, we set them equal to each other like we did when we were trying to derive Charles' law, and we end up with the same question. Same equation. P1 times V1 over N1 times T1 equals P2 times V2 divided by N2 times T2. And there's our assumptions. We assume that P1 equals P2, P1 equals P2, N1 equals N2. I didn't show up the explicit math, but P and P on opposite sides of the equation will cancel, N and N will cancel, and we're actually left with Charles' law. So again, like I said, you had two choices. One, you recognize that, yes, it's a Charles' law question, but that's me. I would not have recognized right off the bat this is Charles' law. But we were able to derive Charles' law from simple assumptions. So let's just plug it in. We're solving for V2 because that's the volume of our condition 2 when we change the temperature. What I did was isolate V2, so I multiplied both sides by T2, so T2 comes over here. Then we plug in our units. We have liters, Kelvin over Kelvin. The kelvins will cancel and give me units of liters. That makes sense because I want my volumes in liters. Solve for the equation and apply significant figures. There's 3 sig fig here, so my answer should be in 3 sig fig. I have 5 here in terms of sig fig, but since they're multiplied, the one with the lowest sig figs determines the total number of significant figures in your final answer, so we end up with 804 liters. All right, so that was a lot. So hopefully, it wasn't that much, but it was a lot to process all at once. It's a new concept. So if you think about it, we actually only did 2 problems, but there's a lot of thinking involved, and learning that critical thinking is really, really, really going to be beneficial throughout this entire chapter, and critical thinking is one of those things where it's always going to benefit you through life. So hopefully you start to learn this process of how to attack a problem, even if you're a little bit unsure, rather than just having a scaffold. So if I have this problem, I do this equation. If I have this equation, I have to answer these problems. We just answered a problem totally just from assumptions and from just one equation, right? Where is that? Right? So this is what I'm saying. Start to get more comfortable with critical thinking rather than just asking, well, if I'm given this type of problem, this is how I answer it. So I answered that with just very little assumptions. All right, so why don't we move on a little bit? So we've already talked about the ideal gas law, how to derive the other gas laws from the ideal gas law, and we also did an ideal gas law problem. 2 of them, in fact, right? So let's see other ways we can tweak this one equation that we know to gain more useful uses, or I guess it's kind of a little bit redundant, but more uses out of this equation. So let's start with what we have. PV equals nRT, right? That's our ideal gas law. Let's isolate N and V on one side of the equation. So what I'll do is I'll divide both sides by V. So that means N over V, divide both sides by RT. Now I've isolated N over V on one side and P over RT on the other. So you have to trust me just for a second on this one, but you're going to see how the math works. So if we multiply both sides by the molar mass, so we got to remember what our definition of molar mass is. That's the number of grams a substance weighs if you want to get exactly 1 mole of that substance, right? So we know that carbon-12 is the basis for the atomic mass unit, when we know atomic mass units also equivalent to grams per mole. So if you massed out exactly 12 grams of carbon-12, you'd have exactly 6.022 times 10 to the 23rd atoms of carbon, which is 1 mole. So that's what we're going to. Again, we go to the periodic table, figure out the number of atoms that are in our molecule to determine the molar mass. So let's take a look at what math we're doing here. So we have our original equation is our N over V, P over RT, and we're multiplying both sides by the molar mass, right? Remember your algebra rules, we multiply both sides of the equation by the same thing. It's not affecting the numerical value, but it can help us try to eliminate some variables we don't need. So let's look at the left-hand side of the equation. So right now, there's our right-hand side of the equation. It doesn't change. We just put MP, because we times the M, the big M, molar mass, times this quantity. The M is on the top, but it's in the numerator, so that's pretty straightforward. But let's take a look what's happening over here on the left-hand side of the equation. So all I did was take my molar mass, my number of moles, and my volume and broke it down into its respective units. So we know molar mass is a complex unit, it's grams per mole. Well, there's my N, which is in units of moles, and right now we're just leaving V in volume, and you'll see why I did that in a second. But we'll also notice right here, moles and moles can cancel. So let's take a look what happens. Well, on the left-hand side of the equation, we're left with units of grams per unit volume. Doesn't matter what my volume is, but grams per volume equals the molar mass times the pressure divided by R times T. Well, let's think about that. Density is mass per volume, so that G over V on the left-hand side of the equation can be represented as density. So density equals the molar mass of a gas times its pressure divided by the universal gas constant times T. So that's a lot of talking, but it ends up being a pretty simple and straightforward equation. All I did was take PV equals nRT and multiply it by the molar mass. We proved mathematically that the density is then related to that equation through this new equation. So let's see, well, the reason we're actually showing this slide is because you guys will be doing this next week in lab. So I want you to see explicitly why we even went over this equation, where we show that density is proportional to the molar mass and the pressure and the universal gas constant in T. But if we rearrange the equation, there's our molar mass equals the density times the universal gas constant times the temperature, and specifically the absolute temperature, so in Kelvin, divided by the pressure. So let's use that. So the question is going to ask us, what is the density of carbon tetrachloride vapor at 714 torr at 125 degrees Celsius? So again, even though it's a simple problem, let's start getting into the habit of making columns. So we have our givens, our finds, and our equations. So our pressure is given to us. It says it's 714 torr. Our temperature is 125 degrees Celsius. I've automatically gone ahead and just said I'm dealing with gases, so let's jot down R. It is specifically asking us to find the density of carbon tetrachloride. And again, kind of a scaffolded question. I wrote down the equation for density equals molar mass times pressure over RT. Immediately, what you should recognize is that since this is the R we're going to continuously use, it is not common to use it with, say, liter torr per mole Kelvin or liter torr per mole degrees Celsius. This is the number we're going to pretty much stick with. So that means the other variables we have, we should be converting those to units that correspond with R. So let's do that. Let's take our 714 torrs, which is our pressure, use dimensional analysis where we know 1 atmosphere is 760 torr, convert that to atmosphere, 0.9395. You'll notice that I didn't apply significant figures. The reason for that is because this is an intermediate equation. So this number I'm going to use again to get a final answer. And if I applied significant figures early, it tends to compound the error. It's not absolutely necessary to do in Gen Chem, but as you go further in your career as a scientist, it's really good to get used to this. So I'm gonna continue with this. So we're not applying significant figures. At the very least, we're giving one extra significant figure. But we will, in the final answer, we'll have correct significant figures. Then we have our temperature. It's 125 degrees Celsius, converting to K, so 398.15 K. We'd also need to know the molar mass of carbon tetrachloride. So again, this whole course ends up being cumulative, so we need to know carbon tetrachloride. If I'm given the name, I need to recognize what it is. So the first thing that would give it away, if you notice, A has carbon in it, so it doesn't have a metal in its first name, but it also has a prefix of tetra. So we know it's a molecular compound. So that's telling me I have carbon tetrachloride. So there's no other prefix in front of carbon, so it's automatically assumed to be mono. If it's the first word, we omit mono. So that means we have one carbon. Tetra is 4. Chloride corresponds to the chlorine atom. So we have carbon tetrachloride, CCl4. We go to the periodic table. We have one carbon. It weighs 12.01 AMU. Chlorine weighs 35.45 AMU. Multiply them together, 12.01 AMU plus 141.8 AMU is 153.8 AMU. And then we know AMU corresponds, even though this is dealing with one atom, if we have 1 mole of CCl4, it weighs 153.8 grams per mole of CCl4. So now we have pretty much everything that we need. Well, there's our molecular weight, there's our pressure, there's our R, there's our temperature. One thing you might notice here, and I think we've gone over this in class before, where I say mole raised to the negative first power. Anytime you raise something to a negative power, it's the same thing as dividing. So this actually means 153.8 grams per, so divided by mole. But it's just an easy way to write everything on one line. I could have done the same thing down here. I could have made it liter atmosphere times mole raised to the negative first times K raised to the negative first. All a matter of preference. We do that math out, we end up with 4.42. We're going to make sure we're in the correct units though, so let's do some dimensional analysis. There's our density, not density, our molecular mass, so grams per mole, times atmosphere, that's our whole numerator. Like we talked about before, when you have things in the denominator, it's like multiplying by the reciprocal. So our mole per Kelvin comes to the top, our liter atmosphere goes to the bottom. Over here, again, we're in the denominator, so it stays in the bottom, so 1 per K. So it's the reciprocal of this number, so 1 per K. Let's take a look. Mole cancels with mole, atmosphere is with atmosphere, K with K. It leaves us the grams per liter, so then we need to use units of grams per liter. So even though before we used grams per cubic centimeter or grams per mil, this is why it's important to check your units. So at 714 torr, at a temperature of 125 degrees Celsius, carbon tetrachloride vapor has a density of 4.42 grams per liter. We can kind of make sense of this. The reason for that, if we go back and take a look at our general equation for density, first off, air, I don't expect you to know this off the top of your head, would have a density somewhere around, I think it's 1.1, 1.2 grams per liter. And so it says, okay, so that means if we have something around 4 grams per liter, which is a carbon tetrachloride, that means it's going to be heavier and more dense than air. Okay, and it's not a crazy amount. You're saying it's 4.5 times more dense. All right, that sounds reasonable to me. But other information that we can pull out of this, so we look at the molecular weight, it's saying that the density is directly proportional to the molecular weight. So as the molecular weight of a compound goes up, you'd expect the density to go up because it's in the numerator. Gold carbon tetrachloride, we already said, weighs around 154 grams per mole. If we assume air is mostly nitrogen, which it is, which is around 32 grams per mole, that's a big difference. So the density of air should be a lot lower than the density of carbon tetrachloride. So that makes sense, and it's in a reasonable range. And another thing that we can pull out of this equation is also that density is inversely proportional to temperature. And this is not entirely important to use in gas laws, but it also describes physical phenomena that we're used to. So when you think about, well, I'm used to like having helium balloons at a birthday party. Okay, helium's less dense than air. Well, there's one reason why it floats, right? Because helium is a lower molecular weight than air, even though they have the same pressure and temperature, it's less dense, so the helium balloon floats. And the same thing can be said for hot air balloons. Hot air balloons are filled with air. So that means the molar mass of the air around the balloon and inside the balloon is the same, but the temperature inside the balloon is very hot because they have that gas flame going. That decreases the density. So the decreased density of air inside the hot air balloon causes that hot air balloon to float relative to the moderately temperatured air around the balloon. So as the temperature goes down, the density goes down, and that means that gas is going to float. All right, almost done talking about the ideal gas law before we move on to talking about partial pressure, and then we'll wrap up after that, so not too much longer. So let's talk about, so I told you stoichiometry is not going to go away. Let's talk about relating the ideal gas law and the other gas laws, which we've already wrapped up into one idea of the ideal gas law, right? And how that applies to reaction stoichiometry. So let's take this as an example. And so we've kind of done this before. We started with stoichiometry. We moved on to solution stoichiometry. Now, what happens when we're dealing with solution stoichiometry when the reactants are in the form of a gas? So let's take a look at this. It says automobile airbags are inflated by nitrogen gas generated by the rapid decomposition of sodium azide, NaN3, according to the following reaction. It says 2 moles of sodium azide, solid, so it's a white powder. It's going to react and it forms sodium solid plus 2 moles of sodium solid plus 3 moles of nitrogen gas. And it says if an airbag has a volume of 36 liters, so we can immediately assume this reaction happens very, very quickly. So this generated N2 must be possessing a volume of 36 liters because solids only possess basically their very small amounts of volume, especially when you start with a small amount. So the majority of this 36 liters, and we're going to assume all of it is due to the gas, is to be filled with nitrogen gas. And it tells us the pressure of the airbag, which is 1.15 atmospheres. And it's saying that the temperature of the airbag was 26 degrees Celsius. It's asking us to back calculate how many grams of the sodium azide did we start with. And just for a quick anecdote, sodium azide is one of the few chemicals that freak me out because actually it's incredibly toxic. But that's not really relevant to the question, but anecdotal information. All right, so let's attack this. So we know we were given the information in the paragraph, in the question, the word problem. So we break it down. We said the volume of the airbag is 36 liters. The pressure of the airbag was 1.15 atmospheres. The temperature is at 26 degrees Celsius, which we immediately converted because we said it's a gas law. Let's convert it to K. So 299.15 K. Our R, which is our universal gas constant. Again, we pretty much keep using this number over and over again. Again, we notice what our units are: liter, atmosphere per mole Kelvin. Liter, atmosphere, Kelvin. Good. Awesome. Or at least everything that we were given is in the correct units, so it makes our life easy. We're going to remember what the question asked us to find, which said how many grams of sodium azide must be decomposed. So the mass of sodium azide, that's what's asking us to find. And again, we could list a couple of equations, but let's keep it simple. What equation, what we might think we might use? Let's try the ideal gas law. PV equals nRT. So let's think about this. Everything that was physically being described in the airbag was describing the nitrogen. So we're describing this part right here. We know we had a pressure associated with the nitrogen, a volume associated with the nitrogen. R is always R, and we gave a temperature associated with the nitrogen gas. Everything was held within that airbag. So that means we are solving for n, and maybe I should have written this down explicitly, but this should be n sub n2, so the number of moles of nitrogen gas involved in this reaction. So let's plug in our numbers. We knew what the pressure of the atmosphere, the pressure of the nitrogen gas was, 1.15 atmospheres. It filled the volume of 36 liters. I just wanted to make sure. It seems pretty big, but it actually kind of makes sense. We have our R, and then we have our K. We plug in the numbers. PV equals PV over RT equals N, and we should come out with 1.686 moles of nitrogen gas. And we're still not done because that does not answer what it was asking us to find, which is mass of sodium azide. But we do have this part of our chemical reaction, which means we could use the molar ratio between nitrogen to sodium azide. So let's do that. If I know at the very end of the reaction I had 1.686 moles of nitrogen, I use the ratio between 3 to 2, so every 3 moles of N2 produced, 2 moles of sodium azide are consumed. So at minimum, to produce that 1.686 moles of N2, I had to have started with 1.124 moles of sodium azide. Well, it didn't ask me for moles, it asked me for mass, so we need to keep going one more step. 1.124 moles sodium azide. We'll use the molecular mass of sodium azide. It should give us the number of grams of sodium azide we need to start with. In applying significant figures, it's 73 grams of sodium. Oop, I wrote sodium nitrate, sorry. That should be sodium N sub 3, not NO sub 3. So sodium azide. The reason why it's two significant figures, that comes from the volume of being only 36. Good. All right. So we've done a lot. We've covered a lot of different ways, at least 3 different ways to use the ideal gas law. Even I guess kind of 4. One was just straight out using it when we were giving 4 of the 5 variables. The other one was to use a comparative example, which was our Charles law example, where we re-derived Charles law based on simple assumptions. And we also used the ideal gas law in a stoichiometric problem. So there's a lot of ways. Oh, and sorry, and there was also that density problem. So there's several different ways we can use that one equation as long as we physically understand what is happening and what the question is asking. So again, my biggest recommendation for when you're trying to do these problems on a quiz or a test, and especially real life, think about what's physically happening, and it can give you a clue on how to attack the problem based on simple assumptions. All right. So we will get back to the ideal gas law. I promise it will not go away. But what we want to talk about now is a little bit more complex situation. So before, we were either talking about a situation in which the gas was, it was a pure gas in one situation, right? So maybe we had that example of an oxygen in a container. The oxygen got hot or it got cold and it changes the volume or it changes the pressure, right? But we're only talking about pure oxygen. What happens when we talk about a container that contains 2 different types of gases? And what we're going to assume, unlike in this last problem where we see a gas being evolved as part of a reaction, or if the gas was reacting to form another product, what happens right here if 2 gases that don't react are combined in a container? And so what you can think about, that's a really good example, think about blowing up a balloon. If you assume air is just mostly nitrogen and mostly oxygen, which is a pretty reasonable assumption, right? You're blowing up that air with nitrogen and oxygen, or assuming you're not exhaling CO2, which you kind of are, but it's just a thought example, right? We can blow up a balloon with air, but it's a combination of more than one gas. So we need a law, or at least a way to model this behavior of how each gas behaves and how it affects the total pressure of that system. So let's read through this. It says, if 2 gases that don't react combine in a container, each gas behaves independently of the other. The total pressure of the mixture of gases equals the sum of the pressures that each would exert if it were present alone. So let's break that down. Let's go back to that second phrase. Each gas behaves independently of the other. So we'll get into this on Friday, but it is one of the definitions of an ideal gas. So you might be questioning, why do we call it an ideal gas law? We're going to come up with a definition of what an ideal gas is, but to be ideal, the gas particles cannot interact with each other. And even if we're dealing with real gases, say like nitrogen and oxygen, we can also make a reasonable assumption that they behave independently of each other. And this goes back to when we were talking about gases in a cylinder, and the space between gas molecules. Relative to the size of the molecule, the gas has huge amounts of space between each other, as long as it's a reasonable volume, not something not like crazy small. So to make the assumption that if you have a mixture of nitrogen and oxygen, to say that most of the time they're not interacting with each other, that's pretty reasonable. So that's how we can get to that part. Each gas behaves independently of each other. Okay, let's read the second part. Then it says the total pressure of the mixture of gases equals the sum of the pressures that each would exert if they were present alone. So we think if we had a container, well, if I had a mixture of nitrogen and oxygen, so if they're not interacting, so if I just measured the pressure of just the amount of oxygen alone, it has a certain pressure associated with itself. So let's think about that as, say, condition 1. So that would be the pressure of the oxygen equals the number of moles of oxygen times R times the temperature divided by the volume that the oxygen occupies. Then we can do the same experiment and say, okay, well, if I took the same amount of nitrogen that was in the mixture and just put it alone, that can be condition 2. So it would be the pressure just associated with the nitrogen equals the number of moles of nitrogen times RT over V. So that means we have a pressure associated with just the oxygen alone, the pressure just associated with the nitrogen. Well, what happens when I take those two samples and put them together? This is exactly what we see. And this is called Dalton's law. It says the total pressure of a system equals the pressure associated with the first gas plus the pressure associated with the second gas plus the pressure associated with the third, and on for infinity, as long as how many samples of gases you have in there will total to the total pressure. So in our nitrogen-oxygen example, we only need P1 and P2, so the pressure associated with the oxygen plus the pressure associated with the nitrogen equals the total pressure. And the way we describe that is we'd say the pressure, oh, sorry, my mouse keeps dying on me, there we go. The pressure total equals, we say specifically the partial pressure due to oxygen plus the partial pressure due to nitrogen. And again, we're assuming it's a two-component system, totals to pressure total. So let's use this as an example. It says we have a mixture of 6 grams of oxygen gas plus 9 grams of methane gas, so CH4, carbon tetrahydride. We gotta look that one up. I gotta look up the IUPAC name. Wow, I can't believe I'm bad on that one. All right, so let's rewind for a second. I'll send you an email with the correct name. I don't know why I'm blanking on it. It says a mixture of 6 grams of O2 gas plus 9 grams of methane, CH4, is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas if the temperature and volume remain constant? And how is the total pressure affected? So let's take a look. It says we're given the mass of O2, which we say is 6 grams. We have the mass of CH4, which is methane, and that's 9 grams. The volume at which everything takes place is 15 liters. And it also says the volume remains constant, so we're not going to give it a subscript, it's just the volume. It says the temperature is 0 degrees Celsius, which is 273.15 K. So we converted immediately. We said gas law, let's go to Kelvin. It also says temperature remains constant, so I didn't give it a subscript, it just describes the temperature of the system. It's asking us to find the partial pressure of each gas, so PO2, and the PCH4, so the partial pressure or pressure associated with O2, the partial pressure of methane, and the pressure total of this mixture of the two gases. Write down a couple equations that we know. We know the ideal gas law, so PV equals nRT. We also know Dalton's law now, which says P total equals the partial pressure of oxygen plus the partial pressure of methane, because it's a binary mixture of two molecules, or two different types of molecules. So let's think about this. Let's break this down into piecewise. Let's just start with oxygen. What happens if we had oxygen under those conditions, where it was just oxygen at 15 liters and at 0 degrees Celsius? A reasonable assumption. We're just going to assume the CH4 is not even there. We'll say, what's the pressure associated under these conditions? So we rewrite PV equals nRT as specifically as the pressure of oxygen times the volume that it's in equals the number of moles of oxygen times the constant times the temperature at which the system is at. Rearrange to solve just for PO2 by itself. So we end up with this equation. But if we look, R, we know is in liter, atmosphere, moles, Kelvin. Well, there's our Kelvin. There's our liters. But we don't have moles of O2. We only have grams of O2. So let's solve for that right away. 6 grams of O2 using the molar mass of O2 gives us 1.875 moles of O2. And again, you'll notice that I have 4 significant figures there for the mole O2. The reason for that is because this is an intermediate mathematical operation, so I don't want to introduce rounding error. So I'll just continue with additional significant figures till the end. So now I know in the condition of 15 liters at 0 degrees Celsius, this is the number of moles of oxygen I have in there. Well, let's plug that back in. Under these conditions, now I know I have 0.0280 atmospheres of pressure associated with that oxygen under those conditions of 15 liters and at 0 degrees Celsius. We need to do the same thing for the methane gas because it's a mixture of two gases. We'll go through the same process, rearrange the equations. We're solving for the partial pressure of methane. Again, we know RT and V, all in the correct units. We do not have moles methane. We go about the same process of converting grams methane to moles methane. Plug that into our equation, and we can solve for the number of moles of methane. Sorry, the partial pressure of methane. We end up with I don't know why it keeps doing that, 0.841 atmospheres. So now we have the partial pressure associated with oxygen and the partial pressure associated with the methane. We go back to Dalton's law because the question was asking us what is the partial pressure of each gas. The second part was how is the total pressure affected. Well, the total pressure is affected because both molecules contribute to the total pressure, right? So the total pressure is going to be PO2, so that's the partial pressure of oxygen, plus PCH4, which is the partial pressure associated with the methane. So we just add them together according to Dalton's law. Here's the partial pressure of oxygen that we originally solved for. Here's the partial pressure of methane that we originally solved for. Add them together. The total pressure at this temperature and volume associated with that binary mixture of molecules is 1.121 atmospheres of pressure. So that was pretty much the long way of going about this. So there's a little bit easier way to break this down. It's a combination of Dalton's law and something new that we're going to learn, which is called mole fraction. And we're going to derive a new law called Raoult's law. So we went through, we understand that, yes, the pressure total of a system equals the partial pressure of one component plus the partial pressure of another component, and so forth until you run out of components. We're sticking with a binary component right now. But what can we do? It says we can relate the amount of a single gas in a mixture and its partial pressure to the total amount of gas and total pressure. That's a lot of words, right? But let's take a look at this equation. What we have on the numerator here is saying it's a regular PV equals nRT, but it's been rearranged so that just the partial pressure of whatever gas 1 is being solved for. So imagine it's our last example. This would be the partial pressure of oxygen equals the number of moles of oxygen times R times the T times the volume. If we compared that then as a ratio to the total pressure, we can say the total pressure of the system equals the total number of moles of the system equals R times T times V. What we'll see is both of these R times T times V cancel out, and we find out this ratio that the partial pressure of component 1 in relation to the total pressure of the system is equal to the molar ratio of whatever number of moles you have of component 1 to the total number of moles in that system. We call this ratio of N1 to N2, so the number of moles of component 1 to the number of moles of the total components. We call this the mole fraction, or chi. So it looks like the letter X, it's the Greek letter chi. So if we ask if we had a mixture of molecules, 1 through I, it doesn't matter, you can have an infinite number of molecules, it doesn't matter. It says chi of component 1 equals moles of component 1 over the total number of moles, and we know that equals, again, we just represent that more simply as the number of moles of component 1 over total moles. Well, let's plug that into the equation, right? So if we know N1 over Nt equals chi, so this converts to P1 over Pt equals chi, which we see right here. Well, let's isolate it. If we're looking for just the partial pressure and a mixture of gases associated with compound 1, it's just we get rid of Pt, throw it on this side of the equation. So the partial pressure of component 1 equals chi sub 1, so the chi, the mole fraction of component 1, times the total pressure. And this should make sense. If you think about it, maybe percentages might make a little bit more sense. That imagine if you had a mixture of air where it's 80% nitrogen and 20% oxygen. That means that the total pressure, or the partial pressure associated with nitrogen, if it's 80% nitrogen, or if it's 80% nitrogen and 20% oxygen, the total pressure associated with nitrogen is 80% the total, and oxygen is 20% of the total pressure, because that's the number of moles. There's 80% of all the moles are nitrogen, 20% of all the moles are oxygen, and so that should hopefully start to make sense. It's kind of intuitive of why the mole fraction times the total pressure is the partial pressure associated with whatever compound you're looking at. So let's put this a little bit into practice, because sometimes, it's easier when I'm showing you guys on the board, but now that I'm lecturing at you through an online lecture, it's sometimes a little, I hope it's clear, but just to give it a more tactile example, let's actually do an example, right? So this ends up being called Raoult's law, which is specifically this P1 equals chi1 times Pt. So let's ask two questions. So I'm going to expand it a little bit more. Instead of being a binary mixture, it's going to be a ternary mixture. So it's going to be three gases. Excuse me, coughing. The first question I'm going to ask is, what is the mole fraction, so chi, right, of a sample of 21 moles of O2 gas, 78 moles of N2 gas, and 1 mole of argon gas? And let's ignore the second part of the question. We'll get to that in a second. So let's just deal with the first part. So it's asking us the mole fraction of, I guess I did not make that more clear. So I was specifically asking, what is the mole fraction of oxygen of a sample of 21 moles of oxygen gas, 78 moles of N2O gas, or N2 gas, and 1 mole of argon gas? Sorry, just to be clear on that. So if we're asking for the mole fraction of oxygen, so chi O2, we know according to just the definition of what a mole fraction is, it's the number of moles of O2 over total moles, right? So we go back 2 slides, right? We're looking at here's the mole of compound 1. Compound 1 just happens to be O2 over total moles. That's going to be our chi. So we know it's 21 moles of O2 over the total amount of moles, which is 21 moles of oxygen, plus 78 moles of N2, plus 1 mole of argon. You add up 21 plus 78 plus 1, made our lives easy, equals 100. 21 divided by 100 is the chi of O2, which is 0.21. And to put this in parentheses, you don't have to put it there, but it is unitless because moles divided by moles is nothing. So the chi of O2 is unitless at 0.21. So let's see how we can use that. So we solve for mole fraction. Let's see how it's important. So the question says, what is the partial pressure due to O2, assuming this mixture of O2, N2, and argon are at normal atmospheric pressure? Doesn't give us a lot going on there. We do know that since it's a ternary mixture, so it's PO2, so the partial pressure associated with oxygen, plus the partial pressure associated with nitrogen, plus the partial pressure associated with argon, has to equal the the pressure total. This is a new phrase, I guess, oops, I had to go that way. That we're dealing with. Anytime you see normal, especially normal atmospheric pressure, it is talking about 1 atmosphere of pressure. So it's saying if it's at normal atmospheric pressure, well, that means total pressure has to be 1 atmosphere. So that's why I have it written here that pressure total equals atmospheric pressure, which equals the sum of all the partial pressures of O2, N2, and argon. So if we think about that, we actually don't even need this top equation. We're only asked to solve for the partial pressure due to O2. So that's going to be due to the contribution that the O2 contributes to the pressure total, which is its chi of O2 times its total pressure. So essentially the percentage of how much O2 there is, but represented as a fraction, times the total pressure. So that's the way you can think of it. Like how much is O2 contributing to the total pressure? Well, it's contributing 0.21 or 21% of the total pressure. You multiply it together. Luckily, it's unitless, right? Not luckily, but it makes sense. So unitless times atmosphere is atmosphere. 0.21 times 1, 0.21. So if we had a mixture in that ratio of 21 moles of O2 gas, 78 moles of N2 gas, and 1 mole of argon gas, at normal atmospheric pressure, aka 1 atmosphere, the partial pressure associated with those oxygen molecules is 0.21 atmospheres. Alright, so that was a lot of talking. That's what I wanted to get through today in lecture. Maybe it's a good thing we had a snow day, because that ended up being about 10, 11, 12 minutes longer than a normal lecture. What I will do after we finish off the lecture on Friday, I will post some additional practice problems because we have our quiz, I believe it is on Monday. But I will make sure you guys have practice problems with this. We'll keep going with it. I highly recommend reading slowly through the book, taking the notes, and then coming back to this lecture. It's kind of hard to take in everything when I'm just giving you everything. Passive learning, it makes a lot of sense at the time, but as soon as it's called the professor effect, as soon as I walk away, or it happens to me all the time with my own professors, you walk away, all of a sudden you're like, uh-oh, what happened? I don't remember. So you do need to be responsible for taking it upon yourself, making sure you understand this, and that you can do these problems without me walking you through step by step. And so that might be my recommendation. All right, good luck. It's only the afternoon right now. Looks like the clouds kind of came in, but hopefully you guys are enjoying your day, and I'll see you guys all on Friday.